Detect and avoid for unmanned aircraft systems, or UAS, is a concept that is designed to help UAS pilots remain safely separated from other aircraft while operating in the National Airspace System. It is an essential requirement for the mandated integration of unmanned aircraft. NASA Langley Research Center has historically been at the forefront of research into cockpit technologies for separation assurance. Detect and Avoid applies similar principles. It provides flight deck-based automation and guidance to facilitate self-separation. At the heart of DAA is an algorithm known as Daedalus for Detect and Avoid Alerting Logic for Unmanned Systems. Daedalus can identify situations where proximate aircraft have become threats and provide suggested guidance in the form of maneuver bands to assist the UAS pilot in remaining well clear of the aircraft.
We started back in 2011 working on what was the first concept where we identified the technology that was necessary to support these operations. We identified the research issues that existed, and then we started developing the simulation environment that was necessary to conduct this research.
Before any element of Detect and Avoid can be considered operationally ready, it must undergo thorough and rigorous testing. Experimental research is an essential part of establishing the minimum operational performance standards for underlying technologies such as UAS communications and control, traffic surveillance data accuracy, and human interface design, to name a few.
One of the challenges in the case of unmanned aircraft is the first thought would be when you take the pilot out of the aircraft is, oh, I've removed human error. But in actuality, no, you don't do that. You actually move where the human error can take place from the airplane to any system that's controlling it. Even in the case of an automated system, the designer, the developer, the programmer, the maintainer, they all have potential errors that can enter the system.
Langley researchers are conducting realistic, human-in-the-loop simulations of UAS traffic integration in various types of airspace. These experiments will assess the performance of Detect and Avoid and its associated procedures.
Southwest 285, turn left heading 140 out of the turn. Low will be 12 o'clock and 900 miles.
What's unique here is we've essentially taken into this laboratory situation sort of a microcosm of the real world. So you've got air traffic controller sitting behind his screen, which is something they do on a daily basis. But here we've got to generate traffic that looks like the real world. So in another room, we've got what we call pseudo-pilots controlling aircraft in that airspace. We've got ground control station pilots controlling our unmanned aircraft so that we can simulate what this would look like to the air traffic controller in the actual environment.
A key research issue for Detect and Avoid is to quantify the well-clear separation distance between aircraft. This distance has no precise regulatory definition, yet it is essential to compute the guidance used by UAS pilots for avoidance maneuvers. The controller acceptability studies are aimed at establishing separation distances that meet air traffic controllers' expectations for well clear. These speeded-up excerpts from the experiments show a dramatic difference in the deviation paths for UAS around a conflicting aircraft. The difference between the two examples is the programmed horizontal miss distance, or HMD. For UAS Banjo 38, the HMD is half a mile. For Axle 16, the HMD is 3 miles. Note the potentially disruptive use of airspace by Axle 16 versus the minimal separation achieved by Banjo 38.
What we're looking for is sort of the sweet spot where the distances are ones that are acceptable but not excessive.
Time, not distance, is the focus of the CASAT study for collision avoidance and self-separation alerting times. For these experiments, the self-separation function of Detect and Avoid is integrated with collision avoidance alerting, adding a second layer of protection. This capability is derived from the existing Traffic Alert and Collision Avoidance System, or TCAS. Assessing the effectiveness of integrated collision avoidance is one of CASAT's goals.
Descend, descend.
Another priority is to investigate parameters known as alerting times. The appropriate time to alert a UAS pilot of a potential loss of well clear depends on factors such as the time to coordinate with air traffic control, UAS communications and control delays, and aircraft maneuvering performance.
How soon should we tell a pilot that there is an impending conflict? You don't want to let the pilot know that maybe 20 miles away there is an aircraft with which there is a potential conflict, because it is far enough that it's not relevant, and if the pilot starts maneuvering so early, it would be disruptive for the airspace. But you don't want to alert too late, because too late then you will create an unsafe situation.
The versatility of NASA Langley simulation environment gives researchers a platform for conducting other experiments considered vital to assessing and improving the performance of detect and avoid. For example, by varying communications delays during the experiments, researchers are able to determine that one-way delays up to 400 milliseconds are considered acceptable to air traffic controllers working UAS traffic. Also, incorporating wind fields into the simulation shows that dataless guidance works successfully in the presence of real-world winds. The results of this research enables capabilities that will allow stakeholders in the UAS community to have increased access to the national airspace system.
The benefits of the work we do is that these capabilities are enabling capabilities. It is without them, there is no hope, there is no way that you can comply with existing regulations, and therefore the process of integration is not going to be possible.